Yes, sir.
So today we are going to talk about timers. Okay, so in this lecture we will be discussing about timers. What are timers? Uh, what we can do with timers, and how to configure a timer for a particular task. Okay, so let's start the lecture. So first of all, before entering into this topic, I would briefly like to discuss few benefits of the timers. Okay, so what are the why we need a timer when we can write a program with a polling approach, that is delay kind of thing? Why we need a timer separately? So till now, what we were doing is something like this. So LED, we were making the LED high. Okay, then we took some delay, and of course delay, we put some numbers in the delay, and then after that we made the LED low, and then again we took a delay and done. So this whole thing was getting repeated again and again, right? So this was not that difficult. We took a number, some number is there, okay, and then we decremented the number, and with when the number becomes 0, we will come out of the loop and then make the LED low. So this was running quite smoothly. But this approach, that means the microprocessor or the microcontroller, in our case, is always busy in either making the LED high, or counting the number, or decrementing the number, then making the LED low, then decrementing the number. So in all this event, the microcontroller is always busy. Okay, and that means the microcontroller cannot focus or cannot look into any other task. So this delay part is, we can say, is not a very important task to be done. This can be given to some other device which can manage this thing. Anyway, we know that this particular technique is called polling technique. Okay, and polling technique means giving a number. Sorry. Okay, polling technique means giving a number to the microcontroller and ask it to uh, repeatedly decrease the number and keep on doing the same task. Apart from that, what we can do here is, in this case, when we are talking about timers, so there are dedicated timers inside the microcontroller. Okay, so timers means these devices can do two types of tasks. One is they can either count some events, okay, count some events, and secondly, they can generate time based events. When we say count events, for example, like this, you have a microcontroller, a switch. Assume I am keeping it pull up, and then now this can go to a timer or counter. We can call both. Okay, so timer some slash counter, and whenever this switch is pressed, we can check that event and we can count that event. That is the job of counter. So event is switching. Okay, so switching is our event, and we are just counting it using the same device timers. Secondly, what we can do is we can use the timers. Okay, same timers, timer slash counters. Okay, and we can connect this to one of the GPIO pins. Not necessarily that it should always go to the GPIO, but in our case we are talking about GPIO. So it can go to the GPIO and it can generate some event, a pulse or a train of pulse, like a square wave generating function or pulse width modulation based functions. Okay, So, and apart from that, generating interrupts and all at a particular time or particular event. Okay, so these things can be done using timers. So what is the benefit of using this particular device instead of using delay? So previously we were using delay, okay, and this was using polling technique. And of course, we were feeding some number and then the number goes to the register and keep on decrementing, then decrement the number, keep on go back and decrement the number again and again. So this technique was consuming all the resources of the microcontroller. That means it was keeping the microcontroller busy, always busy. Okay. So microcontroller was not able to focus or to give services to other events or maybe other devices because polling will keep it busy. So what we can do is microcontroller can use the timer. Okay. So microcontroller will use the timer and load a number to a timer. The same number, almost the same number which we were using for the delay, a particular number to the timer, and then say, okay, start. Okay. So after a particular time it will set start, and then after loading the timer and saying start, the microcontroller can forget about the timer because the timer's job is to keep on decrementing or incrementing the number. So whatever the delay was doing, the same timer will manage that thing. And at the end of the count, for example, suppose microcontroller entered 500 here in the timer, okay, and then said start. So there can be multiple types of timers, like one is called up counter. There can be down counter. Okay. So up counter, down counter. For example, now here we have 500. So we can use down counter and the count will go like this, go in decrementing. Okay. And it will go up to 0, which is the terminal count. Okay. It will reach 0. So 500, it started the journey from 500 and reached up to 0. And then it, at the end of the event or at the end of the count, it may generate particular pulse, or even it can generate interrupts that to inform the microcontroller that okay, I have completed my task. And there are facilities like it can auto reload after getting or after reaching 0. It can either generate interrupt or it can generate or it can auto reload the count. Okay, auto reload the count and so on. And then the counter will keep on repeating the event. So after every particular interrupt, after reaching the terminal count, it can go to generate an interrupt or auto reload. This is down counting. Okay, this is down counter. Up counter, what we will do, we will enter a number into the micro timer. Microcontroller will enter number into my timer, and the timer will start its journey from 0. Okay, and keep on incrementing the count just like the delay. Okay, and it will reach to the terminal count. So terminal count in this case will be 500. Okay, and it can start from 0. So this is our up counting. So this is our up counter, and here we have the down counter. Okay, and similarly at the terminal count, it can generate either interrupt or auto reload, then renumber, or it can go to 0 next and then keep on repeating the same counting. So this way the microprocessor or the microcontroller, okay, is able to focus on other tasks, other devices, other peripherals, and leave the timing related jobs to the timer. And of course, when the timer reaches to its terminal count, it will keep on informing the microcontroller that okay, I have reached the terminal count. Do you need to generate a particular pulse or generate an interrupt or generate an event like making an LED high, and then after recount and then at the terminal count make the LED low, or so on. So this way we can intelligently use the timer peripheral and reduce the load on the microcontroller. So timer is our peripheral. Okay, and definitely timer, this peripheral, especially this peripheral, timer peripheral, is one of the most complicated and detailed device, and it needs well lot of okay device or peripheral. So you need to have a very sound knowledge about the peripheral. There are lots of registers in these timers. Okay, and then there are so many bits to control to make a proper timer. But once a timer is set up, then you don't have to worry about the the microcontroller can go and it can do another jobs, or it can give its resources to another peripherals like ADC, DAC, or some other devices. So this way, timing related events can be managed by the timers. Timing based events, it can be even counting based events or timing based events. So both are managed by timers itself. Till this part, any doubt? What are timers? What are up counter? What are down counter? At the end, what the timer will do, whether it will reload or it will generate an interrupt or a pulse. And then what are the other features we can explore in the timer and so on. Any doubt till this part? Any doubt in this part? Hello?
No, sir.
No, no doubts. Okay. So let us continue with the timer. What are the things that we have to keep in mind when we are dealing or working with the timers? First of all, timers in the microcontroller TM4 C123GH6PM are basically programmable. Programmable means there are so many things which can be programmed and according to which the timer will behave. So you can program the timer in so many different ways depending on the registers and their bits. So what are the timers that can, what are the jobs which the timers can do? One is, like I said, it can count the events like switching. If you are making the switch on or off, or if there is a sensor which is getting some pulse after a certain time, it can keep on counting that also. So counting events. Secondly, timer can generate external events like making pulses high or pulses low or depending. Okay. Apart from that, these timer can internally trigger or activate or make ADC work on or work off. So you can say that, okay, if there is a sensor connected, for example, we have a microcontroller, okay, and we have a sensor connected here. Okay, sensor. So now the sensor is reading some analog values. Okay, analog values are coming to the sensor, and this sensor is reading the analog value and converting it to digital value. So definitely this sensor will use ADC. Now the ADC will take some time to convert these analog signal to its digital equivalent. It is not that it will simultaneously change at, for example, at time t0. If it is getting the signal, then it cannot generate the output also at time t0. It will take some time t1, okay, t1 or t0 plus delta t. After some time, it will generate the output. Okay, so now this time consumption is important for an ADC. So what the timer can do is, timer can even give this time to the ADC that, okay, if suppose that the ADC is taking 10 nanosecond, assume 10 nanosecond, okay, millisecond. milliseconds. Okay, it takes 10 milliseconds to read one data and convert it to its digital equivalent. So it will read the analog data and it will convert to digital. So it is taking 10 milliseconds. So the timer, what can the timer do here is timer can check or interrupt or read these values or activate the ADC or generate events which can read the ADC after every 10 millisecond. So it can trigger the ADC whenever you need to read or change analog value to its digital. Okay, so timer can of course not only inform the microcontroller, apart from that timer can even work with internal peripherals like ADC in this case. Okay, so this is one of the major advantage of using a timer. Remember, ADC will not convert the signal very moment itself. It will take some time. Okay, and therefore timer can apply that wait event and then read the data, apply again a wait event, read the next data, and so on. So this is very important. Okay, so what are the different types of timers which are available in the microcontroller TM4C123GH6PM? So there are three types of timers. Okay, one is your system timer. We call it Systick. Then it has got a general purpose timer. We call it Gptm, general purpose timer. And then it has got third timer, which is called PWM timer. So these are the three different timers which are available in our microcontroller. Apart from that, if you are working in any other microcontroller, might be possible you may find another timers also. But in this case, we have three types of timer. One is Systick, then is Gptm, and third is your PWM timer. So Gptm is this particular timer provides the maximum programmable features. Sorry. So that means this timer can be programmed to do tasks or events in many different ways. So this is the best timer. But of course, when you are going for Gptm, it will require lots of registers to be programmed to make it work. Okay, because like I said, it gives you the maximum flexibility to program. Okay, so first of all, let us go through the Systick, and might be possible we will look into the Gptm. But in this course, it is not possible to cover all these features on all the programs related to PWM and all. But of course, you know how to go and search the data sheet, write a program depending on the initialization and all. So we will not be covering this part. We will be covering Systick timer and Gptm. And of course, I'm not saying that we will be covering all the features of Gptm. Okay, we will explore what are the possibilities to program, what kind of programs we can generate using Gptm. First of all, we will talk about Systick timer. Systick timer, we can say system timer also. Okay, this is the system timer which is connected to the microcontroller directly, the crystal which is connected to the microcontroller. Systick timer basically, okay, is a simple 24-bit clear on write, okay, decrementing wrap on zero counter. So what are the features here? One is it is 24-bit. So you can enter a number which can be up to 24-bit. Okay, 24-bit means max starting from 000000 to FF. Okay, so this is the max range that you can enter. And based on the system timer, remember it is a decrementing timer, so it will keep on decrementing move towards zero. It is clear on write. That means suppose you have entered a number 500, okay, and it is decrementing like this, and it suppose it reached somewhere around 350, and it has 0 is here, okay, and here at this time suppose you wrote a new number. Now, suppose you entered 600 in this time. So what will happen? This count will stop and it will reload with 600. So it is clear on write. So whenever you write something on this particular timer, it will clear the previous data. Okay. So this you have to remember, and wrap on 0 because that's the terminal count. We can say this is our terminal count. Okay. Done. So clear, it is a 24-bit timer. Which one? Systick 24-bit, clear on write, decrementing, wrap 2 or wrap on 0. So the number or the maximum count in decimal is this one, and this is FF is in hexadecimal. Okay. So this is the basic definition of Systick timer. Of course, it can be used where we can use this particular timer. It can be used for real-time operating systems or real-time events to be generated. Okay, so RTOS mostly works with this. Whenever you will study about real-time operating systems using embedded systems or microcontrollers, then you will find that almost all the RTOS will be revolving around timer-based events or timing-based events, because there the time is more important. At a particular time, you have to generate a particular event, or you have to check a particular event. So RTOS is all about timing, real time. The constraint is time. It is not whether it is performing well or good or bad. The time based event has to be generated. So RTOS tick timer can be used. Systick timer can be used for RTOS tick timer, which can trigger, okay, at a programmable rate and invoke Systick routine. For example, this is our clock running. Okay, suppose our clock is running like this, and we are planning to design an RTOS based system. So in this time, you first check the airbag, assume. First you check the airbags. So there is a function which is airbag, and it will check the airbags function. Then in this event, so that means the airbag function has to be written in such a way that it should be completed in this particular time, because the time-based events are important in RTOS. So after some time, there can be another event which can be checked here, like whether the brakes are working or not, brakes are proper or not. So in this way, this kind of systems can be designed using Systick timer. Okay, so program, and we can call it these airbag, brake, whatever feature, other features you are checking. These are our Systick routines. Systick routines. So this is how we design our RTOS based, most of the RTOS based applications. There the time is important, not the completion of event or whatever. So by the next event, you have to be ready. So you have to make these functions in such a way, or write this function in such a way that they should be completed within the period for the next function to be read. Okay. Now, of course, Systick can be used for generating alarms. Okay, you can change the rate of alarm, that means the speed of alarm, and of course the signal timer also. And you can use the Systick as a simple counter. Okay, counter like switch or event or particular sensor based things. So it can be a simple counter to measure time to complete a particular event and the time used by that particular event. So timer based events checking and all, measuring timing based events. So it can be a counter, like I said. Now, basically, this is one of the simplest timer in the microcontroller that we are using. It has got basically three registers, most importantly, three registers. One is your Systick control register and status register, control and status registers, you can say. So Systick control and status register. Secondly, we have Systick reload register, where you can call it reload or load also, where you will load the number into this particular register, because that number, like I said, 24-bit number you have to write in the register, and it will keep on decrementing from that number. So Systick reload register. And then, of course, if you want to read what is the current status or what is the current count. Okay, for example, if the microcontroller is counting from 500 and Systick is counting from 500, and suppose you want to read what is the count at this particular time. At this particular time, what is the count? Okay, count at this particular time. Then, of course, you can use the Systick current value register. Okay, so these three registers are most important registers to configure the Systick timer. And let us briefly try to understand how can we generate particular time based events at a very particular time, and what is the maximum accuracy that we can achieve, what is the maximum delay that we can generate, and so on. So first of all, system timer or Systick clock, or the microcontroller that we are using, TIVA-C board. Okay, in the TIVA-C board, the microcontroller is connected with a 16 megahertz crystal. Okay, this crystal oscillator is 16 megahertz. Okay, if suppose tomorrow you are having another oscillator connected to the board or microcontroller, then in that case you have to keep that particular frequency in your mind when you are writing a particular program for Systick timer. Therefore, in 1 second, because it is connected to 16 megahertz, in 1 second, the microcontroller can count up to 16 into 10 to the power 6 pulses or clocks. Okay, so in 1 second, you have 16 into 10 to the power 6 clocks. So that means if we come to the calculation, 1 second, you have 16 into 10 to the power 6 clock. Okay, or you can say, because it is starting from 0, remember the maximum number that you can load to Systick timer is 16 into 10 to the power 6 minus 1, because this one is representing, because it is starting from 0. Okay, so 1599999. Yeah, so this way we can use the Systick timer. Secondly, apart from that, if you want millisecond based accuracies, okay, then of course you can use the millisecond based accuracies. And in that case, we know that 1000 millisecond will be 1 second. Okay, that requires 16 into 10 to the power 6 clocks. So 1 millisecond, if you want to generate a 1 millisecond based event, or generate a square wave with a 1 millisecond delay, okay, then in that case, you need to load the count or load into the register 16,000 minus 1. Okay, because these three divided by 16,000 into 10 to the power 6. So this is the time. Similarly, if you want microseconds delay, so 10 to the power 6 microseconds is 1 second, and that is equal to 16 to 10 to the power 6 clocks. So 1 microseconds event, if you want to generate, then you will have to load 15 into the load register. Okay, these are in decimal, and of course you will have to convert it into hexadecimal. Okay, clear. So these are the things you have to keep in mind, and these calculations have to be there in the mind while we are programming the Systick timer. Till this part, any doubt? Any doubt till this part? If not, okay, let's go and check what are there in the registers, and how can we read those registers. So first of all, like I said, the first register which we will be using to program the Systick timer is Systick control and status registers, and it is also known as STCTRL. Okay, and in that we have D16, D2, D1, D0. These are the most important bits. So what is D16? It will use, it is used to generate load the count. Okay, so whether the count is reached to terminal count or the final 0 or not, okay, we can use this particular bit 16, D16. So if it is 0, let me go to the register and show you that. So you go to the Systick control register. So first is this particular 16. So there are 4 registers which are allowed to be read or written. But here you can see here 16 is R0. Sorry, RO. RO means bit 16 is RO. Means D16 bit is for which purpose? RO stands for what? Hello? RO is representing what? RO.
So register
Read
number
only.
0.
No, 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 no.
Read only, sir. Read only.
Read only. So user cannot write in this particular bit. User can only read. Please read only. Whereas if you come down, like see here, RW, RW, RW. So these are read and write enabled. So you can read them or even you can write them. Okay, so first of all, count 16th bit in the system control register. What it can do for you? If it is 0, the Systick timer has not counted to 0. That means the count has not reached to the terminal count. Second, if it is 1, if this bit is 1, who will write 1 on this bit? Who will write 1 in this particular bit? Hello? Who will write this 0 and 1 in this this particular bit?
So
Any
system,
idea? No, no, no. Who?
system,
System. What do you mean by system? System. No, it's not the most appropriate answer. Who will write on this particular register? Look, any particular register, either the user can write or who can write on the registers? Microcontroller. Okay, system is not appropriate answer.
Okay. Yes,
Microcontroller.
sir.
So the microcontroller can write on this thing. So if suppose you have entered a value 500 and the count has been started. So then 500, 499, 498, 497. So till that time period, till you reach to 0, this particular bit will be always 0. That will tell that, or that will inform that this particular count has not reached to the terminal count. The moment you reach to the terminal count, which is 0, so the count was started from 500. When it will reach 0, this particular bit will become 1. And you can read here, the system timer has counted to 0. Okay, so if the timer has reached to 0, then this particular bit will be 1. So you can use this bit, you can read this bit to check whether you have reached to the final terminal count or not. So one information you can generate from this bit is whether the count has been 0 or not. First thing. Second thing, we have three bits, 0, 1 and 2, which are enable, inten and clock SRC. So the name itself is more clear. Okay, you can understand that. So clock source. There are many ways by which you can generate a clock. One is the system clock. System clock means the oscillator that you have connected to the microcontroller. Okay. Apart from that, there is an internal circuit which can generate precision internal oscillator divided by 4. Okay, so there is an internal oscillator which you can use and divided by 4 if you are making it 0. then you will be using this particular oscillator, or if you keep it 1, then you will be using the external crystal oscillator that you have connected to the microcontroller. So of course, we will not be going for this particular complicated timer. Rather, we will prefer to work with the system clock, because system clock, we know it is 16 megahertz crystal oscillator which is connected. Clear. Third, interrupt enable. So that means at the terminal count, like I said, you can generate events, you can generate interrupts also. So at the terminal count, when you reach 0, whether you want to generate an interrupt or not. So if you keep it 0, if this bit is 0, then interrupt generation is disabled. So that means when the count reaches to 0, there will not be any interrupt which will be generated. Apart from that, if you keep it 1, then of course interrupt is enabled. And of course, who manages all the interrupt in the microcontroller? NVIC, Nested Vector Interrupt Controller. There is a total separate section for this particular interrupts. So NVIC will manage that thing. So interrupt is generated to the NVIC when the system clock counts to 0. And depending on the type of interrupt you want to generate, you can write an interrupt service routine. When we will reach to the interrupt, we can discuss about this part. Okay. So simply, if you want an interrupt, you make it 1. If you don't want to generate an interrupt, when you reach the final count, you keep it 0. So this is programmable by the user. Last but not the least, 0 bit 0. Bit 0 means enable. Enable means, of course, whether you want to enable the count or not. So counter is disabled. If you make it 0, then the counter is disabled. And the moment you make it 1, so it enables the Systick to operate in multi-shot way. Anyway, don't have to worry about that. But anyway, keep in mind, if it is 0, the counter is stopped. And if it is 1, the counter starts, or the Systick starts. And then, of course, when the Systick will start, it will check what is the reload value or the count value and all those stuffs. And of course, if it has to generate an interrupt or not, whatever. And at the terminal count, does it have to auto reload or not? This kind of functionalities we can check from the other registers. But this register, it gives you the information about these 4 properties. One is whether the count has reached to the terminal count or not, whether you want to use the system clock or precision in oscilloscope divided by 4, precision oscillator divided by 4. You want to generate an interrupt or not, or whether you want to start the counter or not. So this is control, to control the Systick timer. Okay. So these are the 4 bits I have discussed about it. Now, coming to the next register, Systick Reload. So remember, this is a 24-bit counter. So you can maximum load up to FF. Okay, this is the maximum count that you can load. Okay, so this register is used to load the count. Okay, so this register specifies the start value to load into the Systick current register when the counter reaches to 0. Okay. Systick timer can be configured as a multi-shot timer. That means it can repeat over and over, or it can auto reload itself when it reaches to the final pulse or 0 or final count. Okay. Now, if the interrupt, if you are required to generate an interrupt after every 100 clock pulses, remember you have to enter 99 because the count starts from 0. Clear? Okay, this thing you have to remember. If you want 100 clock, then you must keep 99 in that, because 0 is also counted. Okay, 99. Okay, so D3 to D0, D23 to D0 is your 24 bits in which you can load the count. So if you come to this register, you can directly go and check. Only 23 to 0 are allowed. Okay, rest of the bit positions are reserved for future implementation. So 24-bit number you can enter in this register, and that will be the count. It will count from that value towards 0. Okay, then, and This is called reload register because it can keep on auto reloading itself. Okay, done. Okay, last but not the least, you have the Systick current value register. So this register contains the current value of the counter. Like I said, if you, what happened, anything wrong, is it, do you have any doubt? Or okay, no issues. So it will keep on, if you want to check what is the current count, then you can read this particular register. So this is again D23 to D0, 24 bit register. Why we cannot read directly from the Systick reload? Anyone? Because look, if you go through these two registers, okay, let me open these two. Both are almost same. So this is our first register, this is our second register. So you can, I believe you can see Systick reload register, Systick current register. Okay, both are 24 bit and both are almost having the same thing. Only thing is it will keep on reloading. Then why we need this particular register? If we could have read from this register. Any doubt? Anyone? Any clue why we shall not be reading this one rather than this one? Because you could have read this register also, and then you can also know the current status, because this will keep on decrementing or not. Remember, the one of the important line about this particular register when I was stating was it is a 24 bit clear on write. Okay, so you can, whenever you write a new number, it will clear the count and it will stop the count and it will start from that particular new count. But apart from that, okay, reload register is always going to remain same. If you have written 500, then the 500 will remain same here. Okay, it will not change. So there is no sense to read this particular register, because this has to be there so that when it reaches to 0, that means when you started from 500 and when you reach to 0, again the 500 should reload and then go to 0 again, like this. Okay, 500 to 0. So that's why this register is used to check what is the current particular count value. Okay, done. So let us look into the program and try to understand. I hope you have the data sheet with you and you can keep an eye on the addresses. But right now we have the uh, header files, and we are going to use CMSys files, so you don't have to worry about that part. Let me just briefly show you how to, again, one more time, and let me show you how to include the CMSys file and take the benefit of a more elaborate and advanced header file, that is using structures. Okay, so you just start your program. Okay, I will just wait. Okay, it is taking time. Okay, I will not use this particular feature because there are many ways by which you can activate CMSys, but we are going to follow the way which I discussed in the previous lecture or in the last lecture. Okay. Why it is taking too much time? It is going to load all these things. Okay. So what I will do is I will just close workspace. Okay. Done. And let me just show you how to include all those important files. So I will create a new project. Go to C, main. Okay. Then for time being, I will go to the desktop and I will make one folder here. Folder. I will call it Systick, and then inside that folder I will make my project. So Systick underscore timer. Okay, so this project is there. You can work along with me. Okay, so by that time I will go to the folder which I shared with you guys. So IAR files. In this I shared with you these three files: blue folder, purple folder, and then a readme.txt file. I hope you have downloaded and unzipped these three folders. Okay. So let me just allow the system to complete loading. Okay, so my project is ready. I will just check, make it, and I will just give the name to the project, Systick Timer. Okay. And I can see 0 error, 0 warning. But right now, this project is not using any header file as such. So for that, like I said before, go to the folder which I have shared with you in the classroom. Open the blue file. Take all these three files, inc, include, src source, and startup underscore tm4 c123.s. Copy this and come to the folder where you have your project. So for example, I have my project right now. I have created it in Systick. In that, I will just go and just paste it there. Done. I have pasted inc src startup underscore tm4c123.s in the project folder. Go back, open the purple folder, take this include core file and paste it in the project folder. Done. So you have completed the copying and pasting thing. So in short, we can say we have copied and pasted 4 folders: inc, src, startup file, and include core. So these 4 have been added from our side to enhance the feature of or include the feature of CMSIS. Then go to the Systick Timer project, right click, options, device. You have to select the device. Texas Instruments, TM4C, go down, and then TM4C 123 GH6PM enabled. Done. And then in C compiler, go to C compiler, go to preprocessor, click on this particular 3 dots, click to add a folder, include folder. First INC folder has to be included. Okay. Then again click on add, and then you have to take include core. Okay, so we have included 2 folders in the project, inc and include core. Done. Of course, debugger, if you have the hardware, you can go for TI Stellaris. Otherwise, you can leave it for simulator. Okay, done. This is what we have to use to enable to make the CMSIS work. But till now, you can see there is no CMSIS related file or header file included in the project. What we can do, right click on the project, add files. Okay, add files. First add the startup tmc4c123.startup.s file. Okay, that has been added. So the moment you add that folder, you can see here, let me show you. You have one more folder called startup. Here you can see startup underscore tm4c123, and inside that you have the header file and all. Okay, now the object file. Now second time right click, add files. Okay, and this time you have to add from the src, you have to add system underscore tm4c123.c. Done. enough. So this is what we have to do. First of all, we added two folders in the options. In this options, we added in the C++ compiler preprocessor, we added two folders that is both related to inc. So include core and include. Done. Then after that, we included tm4c123.s file, startup file, and then system underscore tm4c123.c file. Okay. And this will allow all these things. So now let me just use the when we can start writing the code. So now you can write include double quotes tm4c123gh6pm dot h. Okay, and then let me make the project. So now the moment I make the project, you can see all the core files have been included. Okay, the header file has been included. Everything is included in the project, so you don't have to worry about anything now. And from here onwards, you can just directly use Systick sys. Okay, remember the shortcut I told you, control and space. So if you put control and space in the beginning, and then if you start typing like sys, so whatever is available with sys will be shown in the list. So you don't have to worry about that part. Okay, so we are talking about Systick, so we will go to the Systick. And then to access all the registers inside the Systick peripheral, okay, we can use this particular symbol, that is minus sign and greater than. Then inside that, you can see there are four registers: calib, control, load, and value. So we have discussed about these three: Systick control, Systick reload or load, and then Systick current value. Okay, and we can use the registers according to our choice. So you go down and press tab, done. And then you can use your code to enter some values into that. For example, just for example, okay, 0x20. So in this way, you can just go for that. And then if suppose you want GPIO related features, so GP control space, okay, GPIO F tab, okay. Then again, you can take this symbol, minus and greater than symbol or arrow symbol, and then you can see all the registers which are allowed or available inside GPIO F peripheral. Okay, you can use all these registers like data, DEN, DIR, okay, commit register, alternate function select, ADC, and all those stuff. Anyway, so this way you can simplify the programming related issues. Okay, I hope you have understood how we are going to this particular library and using the library's facilities. Any doubt till this part? No. Very good. Okay. So I will go to the example file. Okay. I will use the example project. So let us, don't just believe that you are going to use this particular header, rather use the CMSys. Okay, it will provide you the header file also. Anyway, now let us try to understand what are there inside this particular code. First of all, I believe you know why you are using RCGC GPIO. Anyone? Why we are using this particular GPIO?
Sir, to give clock to start that port.
Yeah, so because we are going to use LED to check whether the event has been generated or not, or after a particular time we are making the LED on or off. Okay, so we are going to make the same blinking program, but without using the polling method. That is, take a delay, enter a number into the delay, and microcontroller will keep on decrementing that number, keeping the microcontroller busy. Rather, we are going to use Systick Timer to do that delays function. So first of all, we just like our previous programs, we enabled the clock for the port F. Okay. And then we have informed the microcontroller that GPIOF, this particular bit is output. So 8, like I told you, 2 will be red, 4 will be blue, and 8 will be green. Okay. So this time we are going to make the green LED on or off. It is your choice. You can go for 2 or 4 or 8. So we are telling that the green LED spin is output and it is digitally enabled. So it will get 0 or 1 value. So we have, by these 3 lines, we have configured the GPIO F port, provided the clock, made the LED output, and then enabled the digital functions or functionalities on that particular pin. Done. Now coming down to the clock or timers part. What we are doing here, Systick load. I hope you now understand why I am entering this particular number. 15999999. It is nothing but 16 into 10 to the power 6. That is, if I write it like this, so we are doing nothing but 16, 1, 2, 3, 1, 2, 3, minus 1. Okay, so that means we are going to generate a delay of 1 second. Okay, so we have entered the value to Systick load register. Okay, then we are making the control register 0000000101. Anyone, why we are entering 0101? Why making D01 and D21? Please refer to that control register, CTRL register. Okay. It will make sense after that. Okay. So we are making this particular one and this one, bit number 0 and 2, 1. So bit number 2, 1 means we are using system clock. Okay. We are not using precision internal oscillator for counting the clocks. We will be using the clock from system clock, which is our 16 megahertz oscillator. Apart from that, we are making this particular bit 1. So that means we are going to start the counter. Okay. Done. So we have put that value and we have entered a value 0. Initialize the current register by 0. Of course, it will keep on reloading itself. So it will be 15999 or that number minus 1. It will keep on reloading it. Okay. So the staircase will always be generated. When I say staircase, it will be something like this. Wait, it will be always like this. So you have the count. So after terminal count, that is our 0. Okay. The programmer or the counter will go to the initial value and then it will keep on reloading itself like this. Okay. This is what is going to follow. So here we have 15999999. This is the value here and we will go up to 0. And after 0, again it will reload to the same number. Okay. So the system clock will take 1 second to count from 15999999 to 0. 1 second. It will take 1 second time period. For example, from here to here will take 1 second. Clear? So depending on your choice, now you have the facility to precisely control any event at a level of microseconds. In microseconds, you can check some interrupt, you can check the ADC value or the sensors value, and then you can go to another event, you can check another value, and so on. Okay, so you just have to modify the program. So right now we are, of course, I'm not saying that this is the best program that we can generate using the Systick, but we are trying to understand what is the basic feature of the Systick. Okay, and what we are doing then, if Systick control and 10000, so this is the number. If these two will become high, then after that, why we are using this number? Anyone? Why we are using this number? 0001, 0000, 0000, this one. We are checking the 16th bit. Okay, so we are checking this bit. We are checking this bit, count. This will be 1 when you reach 0. Okay, so if the product of the value of control register and these two, if they become 1 or if they are greater than 0, okay, then in that case, this particular function will be taking place. And what you are doing in that function, you are just complementing the, not here, it should be 0x. Remember, there is wrong here. 0808. Okay, it's not just 8. Anyway, does not matter whether 8 is in hexadecimal or 8 is in decimal. The count will be 8. Okay, it will become an issue when you are using 18 or 12 or 13, which is above A. I hope you understand what I'm saying. Okay, so 8 is below 10. Hexadecimal and decimal both are same. Anyway, it is better to use X because that will give more sense to this number. Okay, clear? So you are complementing the LED. So previously, if it was 1, after 1 second, it will become 0. And after 1 second, it will become 1. So this is the same thing that you are generating using the delay. But what is the advantage in all this thing? In here, the microcontroller will be loading the number into the clock counter or the Systick timer, and then it will leave the timer and go and do other jobs, while Systick timer will manage this whole event. Now this event is not managed by the microcontroller, so at the end, Systick timer will generate an interrupt and then make the LED on, then come back, make the LED off, come back. Microcontroller will be free from polling job. So now the polling job is handled by the Systick. Clear? Any doubt till this part? Any doubt? Okay, I am not showing you the count because all these programs I have checked and they are working, and I'm not showing you the blinking of LED because I will have to set up the microcontroller board and all. From the next class, when we will be doing the class, or we will be taking the lecture in the classroom, we will be able to see all these events taking place. Okay, or otherwise, if you have the microcontroller board, connect it, test it if it is working or not. Okay, done. Okay, done. So Systick timer is over. Now coming to Gptm or general purpose timer. Like I said, it is one of the most complicated peripherals available in your microcontroller board, and of course, it is the most. It has got lots and lots of registers, and of course, in each register you have multiple bits which you can change or program to achieve some particular task. So this is the block diagram of that particular general purpose timer, Gptm. Okay, so it itself shows that this thing is not that simple. But let us try to simplify this diagram and try to understand what is happening here. Okay, first of all, let me briefly explain you the block diagram and then we will go to the Gptm. So you can see here Gptm timer A control. Then you have timer B control. So simply you can say there are two timers, timer A and timer B. Okay, each timer has got some registers available with it. So for example, Gptm, TAPS. Okay, remember this A. Okay, A, A, A. Here these points. Okay, you can change it by B also. So if you see here Gptm, TAPS, you see here Gptm, TBPS, TM, TPMR. So here TPMR, TPR, TPR, and so on. Okay, so all these registers. So if you want to check, it is just mirror image. For this register, these two are same. Okay, then you have these two registers, these two are same, and so on. And this, the topmost, is same as that of this one. Only thing is the name is different. One is TAPS, other one is TBPS. Okay, no, I have made something wrong. So this one, and this one are same. Okay, this one and this one is same. And similarly, you can come down and so on. Okay, so TAILR and you can see TBILR. So almost they have the similar registers. In short, we can say both have six registers. Okay, both timer A and timer B, that are control registers. Okay. Apart from that, there are registers for making comparator related jobs, comparison jobs. Okay, if this number is equal to this or not, if this number is equal to this or not, because Systick timer was just coming down and becoming 0, and then moving up and then coming down and becoming 0. Whereas general purpose timer can be programmed in so many different ways. Like if you focus here, okay, if you focus here, you can make it up counting, you can make it down counting, and apart from that, you can make it up counting and down counting in 16-bit or 32-bit modes or 64-bit mode also. I will come to that. Okay, so there is a comparator for timer A, timer B, and apart from that, it can generate interrupts. Of course, like the Systick timer, here also you can generate interrupt, but these interrupts can be more complicated, more feature rich interrupts. So you can generate very uh, broad way of interrupts using this timer Gptm. Okay, of course it takes a system clock. Here you can see there is a system clock. Okay, it will take the system clock, and then you can have free running timers also. It can keep on free running. That means reload, then again go to 0, reload, again go to 0, or vice versa also, because this timer can make up counting and down counting both. So this is a brief about the uh, Gptm's block diagram. There are so many things you can explore. Please go through the data sheet. So what are the features of Gptm, or what are the things that we have to understand about Gptm? General purpose timer, there are 6, okay, timers, which are timer 0 to timer 5, and these timers can be either 16-bit or 32-bit. Okay, so there are 6 timers which are 32-bit, 16-bit or 32-bit, which can be further divided into like timer A and timer B. If you are individually using them, they can be maximum 16-bit. But if you combine these two, they can become one 32-bit timer also. Okay, so if you want to individually use them, you can call it 16-bit timer, and if you want to combine them, these 16-bit, then it become timer 0. Okay, then similarly, you can use timer 5 as an individual 16-bit timer, or you can use these two timers, combine them to make it timer 5, which is 32-bit timer. When I am saying 32-bit, then it is nothing but the 32-bit count that you can enter into that timer. So it is 32-bit count. You can maximum count can be 32-bit. So this is one set of timer you have. Another set of timer is again 6 timers. You have another set of 6 timers, which are either can be used as a 32-bit or 64-bit. Similarly, just like the above timer setup, you can, if you want, individually use timer 0A, it can be 32-bit. Similarly, you can use timer 0B, it will be 32-bit. But if you combine them, okay, then it will become timer 0, which will be 64-bit. Okay, so there is a facility, either you can use them individually as a 32-bit, combine them to make 64-bit. Similarly, you can take 16-bit separate, or combine them to make it timer 0 32-bit. Okay, similarly, you have timer number 5. So you have timer 5A, timer 5B. Individually, you can make it 32-bit, or if you can combine, you can go up to 64-bit, which is a very big number anyway. So this is how the first thing that we have to understand are there are 12 timers in short, we can say, which are timer 0, timer 1, timer 2, timer 3 to timer 5. Individually, you can either go for 16-bit, combine them to make it 32-bit. Similarly, there is another set of 6 timers, which individually can work as a 32-bit or combine them to make 64-bit. Okay, let us come down to more details. So there are in total 12 timers, timer blocks, we can say. Okay, 12 timer can be divided into 2 groups. First group is normal timer group. Second group is wide timer group. Normal timer group, we will say, or we will call it for 16/32-bit timer. Wide timer will be designated for 32/64-bit timer. So many things to understand or to visualize now. Remember, when you reset this timer, Gptm, okay, then all the registers of the Gptm are cleared, or we can say they become 0. When you reset them, all become 0. Okay, and then of course these timers can of course work like a counter also, just like the Systick Timer /counter. Okay, and then when using timer A and timer B in concatenated mode, that means when you are making or joining them, okay, or combining these two timers, timer A and timer B, in that case, only the timer A control bits must be used. You should not be using the control bits for timer B. Remember, whenever you combine them, we will use the control bits available with timer A to control the 32-bit or 64-bit timer. Because when you combine 16-bit, it will become 32-bit. When you combine 32-bit, it will become 64-bit. So whenever you combine them, remember, you will use the control bits from timer A only. Don't use timer B's control bits. Okay, third thing to remember, during the countdown mode, that means when it is coming down, the terminal count is always 0. The final count is 0. Okay. Whereas when you are counting up, when the counting is going from 0 towards a bigger number, the terminal count in the count up mode is the value loaded in the Gptm interval register, which is Gptm n. N can be A, okay, n can be A or B. So Gptm TAILR interval load register, or Gptm TBILR. Okay, so remember the final count is loaded into this number, and the terminal count will be the number whichever is loaded in this particular register. Okay, remember one more thing, before using these timers, before you use this timer, always turn down the timer. Okay, that means you should not be entering the number, loading these numbers, or any other count or control registers value, keeping the timer enabled. Disable them, okay, before configuring them. After configuring, you should enable them. So first disable, then configure, okay, and then enable. So this pattern has to be followed. Okay. Now let us go to the next slide, this one. So Gptm, not like the Systick timer, Gptm can work in so many different modes. Okay, this is available in the reference manual, table number 11.3. So Gptm, a general purpose timer, can work in several modes. Which are the modes? One shot, periodic, RTC, edge count, whenever you are trying to count the switch, okay, edge count, or even the pulses, train of pulses, square waves pulses you can count. Edge time, time taken to reach from 0 to high, okay, and then PWM. So these are the 6 modes available, and all individual mode can do different types of jobs for you. But out of this, you have to keep in mind only these 3 modes. One shot, periodic, RTC can be used in combined mode or individual mode. Whereas these 3, edge count, edge time, and PWM, cannot be used as a joint timer. In this case, you have to use both separately. Timer A and timer B will be used separately. But here you can combine them, timer A plus timer B. So you can have that means this can be used, these 3 modes can be used either for 32 and 64 bit, but these will be used always with 16 or 32 bit. Okay. Here in these 3 modes, you cannot combine the timers. Okay. So apart from that, this table, you don't have to memorize it, but keep this table in mind. Okay. So it can be either count up or down. All these modes can count up or down, only except RTC. Okay, RTC can go only up. PWM can go only down. Okay, so I hope there are too many data coming to your mind. Okay, but don't worry. So this one shot can be either 16-bit or 32-bit by combining two 16-bit register. It can be 32-bit or 64-bit by combining two 32-bit registers. Similarly, this one and this one. Rest, they are individually 16-bit, 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 or it can be used 32, 32, 32. Okay. Then, of course, there is something called prescaler. Prescaler is nothing but a number which is used to divide the final number. For example, if you are going to load a number 500, so it will take some time to count from 500 to 0. But prescaler, if you are using 4, okay, or you are using 10, simplifying it, okay, then this count will become 50. So prescalers are used to further improve the range of the count, okay, or the delay, in short. These are the things that you can extract from this table, okay. And prescalers can never be used in combined mode. They are always used with individual modes only. Okay, done. Let me show you the steps to, then I will end. Okay. In the next class, we will make the program or use the program. Anyway, otherwise I will share the program with you because I don't have to spare a separate time to show you the program. Okay. So these are the steps required to configure or use the timer. For that, what you can do is simply you can use the, wait, I will show you. You can go to this particular, okay, sorry. You can go to this reference in the reference manual. Okay. Okay, leave it. I'll show you the reference manual directly. So we have the reference manual here. E folder. In 1 minute, I will finish it. Okay. We have the reference manual here. And you can go to the Gptm, that is general purpose timer block. Okay. Chapter number 11, go down and you can go to this particular 11.4, that is initialization and configuration. Go there and here you can see there are 6 modes like we said. Okay, so how to initialize and configure these modes? One shot / periodic timer modes. There are 6 steps to be followed. 8 steps to be followed. And these 8 steps, if you follow them, then you can generate one shot. That means in one time period, it will come to 0 and stop. One shot. It is monostable, you can say. Otherwise, periodic timer, it is just like astable, keep on repeating it. Similarly, you come down, real-time clock mode. You can use these 7 steps to set up it. Edge count mode, edge time mode, PWM mode, done. So these are the steps you have to follow to configure and enable the counting using Gptm. Okay. So I will be sharing with you one program. Okay. And then you can go through the registers which we are using, because this thing is very long, because timer is, like I said, it's very, very long discussion. Anyway, I will share with you one program or 2 programs. Okay. And then you can see how we are configuring these steps. So I'm actually following the same steps which are there in the reference manual. Step number 1, step number 2, step number 3, and so on. Okay. And then I created one project. Okay, I will share with you, don't worry. Or in the next class, we can briefly go through this.